from across the globe, from the centre of aerospace. And now to you.
Thank you for downloading the Aero Society podcast from the Royal Aeronautical Society.
A very good afternoon, everyone. Welcome to this Royal Aeronautical Society Heathrow Branch webinar. My name is William Lee. I'm the Honorary Secretary of the branch and the moderator for today's session. Joining me today is our speaker, William Silverthorne, a PhD researcher at Kingston University, and our branch chairman, Peter Fryer, who will be hosting today's webinar. Before I hand over to Peter, there are a few housekeeping points that I would like to clear out the way. First of all, please feel free to share your thoughts about today's event on social media channels such as LinkedIn or Twitter, and to interact with us. Secondly, if you require a CPD certificate of attendance for your own initial or continuing professional development records, please use the Q&A panel now to inform us your name, and we will email this to you post-event. Your microphone is on mute, but throughout the webinar, we do encourage you to use the Q&A panel to raise any questions that you may have. And you can also interact with us by clicking the thumbs up or like button next to each questions that are being published. Finally, I would like to make you aware that today's session is being recorded and will be made available via our podcast and YouTube channel post-event. Without further ado, let me hand over the floor to Peter.
Hello. Thank you, William, for today's introduction to the virtual lecture by webinar. I'm Pete Fryer, the chairman of the London Heathrow branch of the Royal Aeronautical Society. I'm exceptionally pleased this lunchtime to be able to welcome all of our viewers to this month's 2020-21 season branch lecture presented as a webinar. Thank you very much for giving up your valuable time to act as delegates at today's event. I hope that you've all continued to successfully navigate your life through the COVID-19 virus. I suspect that most of you will now have reached 2 doses of the magic vaccine, and that more of you will have had one and be awaiting your second. The end is in sight, yes! I hope that you and your family are currently in good health. That all said, we await the government's announcement next Monday, the 14th, concerning the COVID precautions, social distancing and mass gatherings in order to allow the Royal Aeronautical Society and our branch committee to make decisions on the future of branch policy and events. Today, the Royal Aeronautical Society's Heathrow branch is pleased to welcome a young engineer, William Silverthorne. From 2017, William studied for an aerospace engineering Bachelor of Engineering degree at Kingston University, specialising in aeronautics and space technology disciplines. He is currently a PhD student at the same university, preparing a research thesis on, and I'm going to read this, I'm afraid, the design and testing of a variable geometry multi-mode ramjet engine intended to remove the need for turbo machinery in air-breathing spaceplane propulsion. William will present his lecture, Spaceplanes, Why Are They Useful and Why Don't We See Them, to us all today. Broadly, he will cover how spaceplanes fly, propulsion systems, including how engines and propellant choices affect how a spaceplane will operate, and what would make them useful in a modern space industry. He'll also talk about how detonation-based combustors may solve some of the problems that are inherent in the spaceplane. So, without further ado, I'll now pass you over to William Silverthorne. William, as a speaker, welcome to the Royal Aeronautical Society's London Heathrow branch. Thank you.
Thank you very much. That's a wonderful introduction. Spoilers there about the detonation propulsion. I'll tell you more about that later. There we go. I hope we can all see that. So yes, I'm Will Silverthorne, aerospace engineering researcher at Kingston University, and this is Spaceplanes. Why are they useful and why don't we see them very often? So to start off, it's probably important to think about what is a spaceplane. So a spaceplane is a spacecraft that combines the properties of an aeroplane and a spacecraft. Flies in space, glides like an aeroplane, and other than that, the definition is a little bit broad, and we don't have enough time to talk about everything that counts as a spaceplane. So for the purposes of this talk, what are we going to count as a spaceplane? So a spaceplane is going to have a few key features. It is going to it is not going to detach any spaceborne components. Once it is in orbit, it's not going to detach any other parts. No service modules or solar panels or something. It will glide under its own aerodynamic powers. It will not deploy parachutes, with the exception of sort of drag chutes or parafoils, and it will be able to land, which is quite important. So that means we've got Space Rider with its service module, Clipper with the service module, Electron with its parafoil, X-38 with its parafoil, and Pegasus, Gemini. None of these are going to be space planes today, unfortunately, because Pegasus can't land, X-38 can't land without a parachute, and Electron isn't very planey, which probably makes a lot of sense. So the next thing to think about is what are these space planes trying to achieve? Are they trying to save money by being reusable? Are they trying to provide a re-entry with nice low g-forces, so you're not going to squish your payload? Are they hypersonic aerodynamic testing vehicles? Are they looking for better cross-range capabilities so they can glide onto a runway without splashing into the ocean? Or are they trying to achieve interesting orbits that you can't get to very easily by flying somewhere before they ascend to space? The chances are the answer to that is yes. Space planes are generally pretty good at some or all of these goals. So it all really depends on how they are launched. So let's go through that. First of all, there we are. First of all, we have rocket launched. So this is the relatively common way of doing things. We have, especially in practical vehicles, but more specifically in the concept vehicles that we'll be looking at mostly today, we have things like the X-37, X-37B shown here in an Atlas V fairing for its first flight. They launch within or on top of a rocket, and they take off vertically using existing infrastructure, which it's all very convenient. You don't have to worry about reinforcing runways. You don't have to think about strange fueling. It all slots quite nicely into the existing infrastructure. The very grainy picture, I apologize for the quality, is actually the Dream Chaser when it was originally shown to launch on top of an Atlas V, which is quite a nice demonstration of this kind of thing. Or Buran on the right here. This is actually a render, and it launches on the side of a relatively conventional rocket. Its engines do not light. I am leaving the space shuttle for later. However, interestingly, the X-37B was originally conceived to fly in the space shuttle's payload bay, which would have meant it's not in fact launched on a rocket, but in another spaceplane, which leads very nicely into the next slide. The next concept being launching spaceplanes from other planes, which splits itself into two other categories quite nicely. We have subsonic and supersonic deployment. So the very common concept is subsonic deployment. So we have the spaceships from Virgin Galactic, which launch on an unconventional looking but subsonic conventional jet engine powered plane. We have the X-15, which I will be counting as a space plane because it went very high, very fast, very early on, and Max, which launched on the AN-225. So these all are taken up to altitude where they're dropped, but aren't really boosted. The carrier, the mothership, doesn't provide a lot of delta V to help it get into orbit. That is in contrast to the supersonic launch, which I know supersonic is sort of an understatement. These things are going very fast when they separate. And we have here as examples, we have Saenger carrying its little Horus spaceplane, which was deployed at about Mach 7, very, very high up. And Mustard, which is a British aerospace concept from a while back, which was 3 identical, essentially, spaceplanes that would fly as a trio and separate one by one, leaving one in orbit and 2 suborbital. These usually take off horizontally, with the exception of Mustard, and both planes usually return and land horizontally as well. The other use of spaceplanes we have is actually as the mothership itself. So we've got Saenger again from another interesting angle, and the late XS-1 Phantom Express, which was designed as a sort of rapid response vehicle which could launch a smaller rocket into orbit before returning. So this is interesting because it's a suborbital spaceplane, rather like Saenger. So this actually makes rather a lot of sense for spaceplanes, because it means you don't have to deal with a multi-stage vehicle, but also you don't have to try and return your upper stage, so it's quite easy to do with current technologies. The next concept might be what people think of when they think of a spaceplane. They think of it takes off, goes to orbit, comes back down again. No dropping of tanks, no dropping off of smaller spaceplanes. These are exciting, but ultimately very, very difficult, and the jury's still out on whether they're actually worth the effort. They suffer from issues with payload capacity and just generally technological nightmares with mass fraction. Interestingly, though, they can be quite easily used as air-breathing vehicles, as we will touch on later. And the final category is the space shuttle. I know it's not a very broad category. However, the space shuttle doesn't fit in very nicely with the other ones. It lights its own engines on launch, but can't really operate without the external tank. So it's sort of just recovering its engines, but it launches vertically, but lands horizontally, doesn't drop any parts in orbit. It's a bit awkward. So it is the space shuttle in the space shuttle category. So all these different spaceplane types need different types of engines. Do we use interesting storable propellants that can be used for months at a time without much thought about it, but have a habit of dissolving your crew? So you see here in the interesting orange onesies. Or do we use solid propellants that are incredibly high thrust, not very efficient, but sort of like the blue touch paper and run style, but are reliable and very good for lifting you off? It's difficult to balance all of the fuel efficiency, thrust, the cost of the mission, the hazards contained within the propellant, and the lifetime of the propellant. So generally trade-offs have to be made. So we'll start with solid motors. They are very useful because they produce very high thrust, which is useful for lifting you off the ground, especially when you have an engine that's optimized for vacuum, which means you produce relatively low thrust when you're at sea level, and your thrust starts to increase at higher altitudes. However, in spite of being used left, right, and center, they are relatively inefficient methods of producing thrust. They don't have a very high specific impulse, a measure of efficiency, and they are quite dangerous because you light the blue touch paper and you run, because there's not much you can do about them when they are lit. So it's generally better to avoid using them for crewed vehicles, but here we are looking at 2 vehicles that were intended to be crewed using them. Next, we have hybrid propulsion. This is something I've looked at over the years quite a lot, and they are often the worst of both worlds when it comes to solid and liquid propulsion. However, they are throttleable. You can turn them off if something goes wrong, and they are significantly cheaper because the ingredients aren't going to blow up on you if they get kicked. So moving them around, machining them, figuring out the internal geometry is a lot safer. However, they're still not very efficient, but they have been used in spaceplanes, which is says a lot compared to the other options that will be shown here. Interestingly, at the top, that is in fact Dream Chaser, which was originally designed to use hybrid rockets that were then used in the spaceships. So a bit of trivia for you there. This is a very old grainy render again, I'm sorry. The next option is storable bipropellants. They're good because once you're up in space, you could be there for a couple of days, you could be there for months. Storable propellants, they don't care. They will sit there in their tanks trying to dissolve things. That is the downside. They are often very nasty propellants because they're usually chosen to be hypergolic. So when the oxidizer and fuel come into contact with one another, they will catch fire. And when an oxidizer hits something that can be used as a fuel, they will usually catch fire, even if that thing happens to be a person or a bit of fuselage. So you need to be very careful with these. That means the fueling and defueling of these vehicles can get a bit expensive. But again, they have flown on the X-37Bs, you can see at the top, or the Space Shuttle, which had orbital maneuvering thrusters fired by hypergolic hydrazine and dinitrogen tetroxide, as you can see on the bottom and in the middle. On the subject of the Space Shuttle, we have cryogenic bipropellants. These are the sort of gold standard of efficiency. They are the most efficient combustion engines we can produce at the moment, and they are very promising. We have at the top the Aerospike engine, which is a whole nother rant webinar, but they are also used in the Space Shuttle's main engine, which will be flying again on SLS, but also more interesting engines like the one on the bottom right here, Max's RD701, which used cryogenic hydrogen and oxygen, as well as cryogenic oxygen and kerosene to combine high thrust, high efficiency, and higher thrust, slightly less efficiency, which worked out quite nicely in concept and test firing, but never managed to fly, unfortunately. Max was the space plane shown on the cover slide for reference. Next, we have air-breathing propulsion. These are my favorite, but I'm a little bit biased. They have the advantage that you don't have to carry all of your oxidizer with you because you can just pick up what you need along the way. It is sort of a broad family of propulsion systems because you've got ramjets, you've got air-breathing rockets, you've got jet engines, you have all sorts of things in the middle. You have air-augmented rockets. They have a variety of efficiencies and effectivenesses, but they haven't managed to fly quite yet, at least not very well, and not on what I count as a proper space plane. There have been a couple of test vehicles. Hopefully that'll change at some point. They are efficient, they are promising, and they have been looked at for a very, very long time, as you can see at the blueprint shown there of the Hotol's Swallow engine made by Rolls-Royce, which evolved into the Sabre engine, which is still being looked into now, being test fired at the moment, which is very exciting to say the least. At the top you have the other option, which I believe this is an image of an air-augmented rocket, really, or an ejector ramjet that produces static thrust with small rocket engines, and as it gets going, compresses air, runs at a very fuel-rich rocket, allowing the rest of the fuel to be burnt in the air. This was looked at to fly the NASP spaceplane from yesteryear, but unfortunately never managed to get off the ground due to insufficient performance. So a little bit more love is required there. Ooh, electric propulsion. Probably not everyone's first thought when it came to space planes. However, apparently, we don't entirely know how or why, but it was on the X-37B. Here it is pictured on OTV5, which came into land in 2017, 2018, can't remember now. These are extremely efficient thrusters. However, they are very low thrust, so will probably be limited to in-space propulsion unless something extraordinary happens. So we have a lot of different engines here. They do a lot of different things. They have their different strengths and weaknesses. So why don't we have the solution to the problem yet? Where are all these space planes? We've got exciting rockety turbojet concepts like Mustard. We have Buran, which was extremely advanced with composite doors and autonomous flight, which is now, one has been squished by its collapse and one has been covered in graffiti. And we have X-33 and Venture Star with their exciting linear aerospites taking off vertically. So what happened to them? It's probably down to the spaceplane curse. Spaceplanes are possessed by the devil. They do not want to fly, and they probably never will. I'm joking. It's probably a little bit more complex like that than that. So what is it? Spaceplanes are an exciting concept, but they have a lot of downsides. Spaceplanes launched by carrier aircraft need to be small enough to fit on a conventional aircraft, or the carrier aircraft needs to be huge enough to carry the orbiter, which then means you need some industrial strength runway to pick them up and put them back down again. You need landing gear that is big enough to carry the fueled vehicle, but also light enough to be carried into orbit or suborbit, which was always a terrifying problem. Hotol had a detachable landing gear that would be going like half the speed of sound down the runway and then just thrown into the houses at the end, I guess, or deploy a parachute. And SSTOs, single stage to orbit vehicles, suffer from an abysmal mass fraction, payload mass fraction, sorry, of up to like 2% on Venture Star, which struggled to get that, compared to 4-5% on a conventional vehicle. And the lifting re-entry of a spaceplane is an advantage for bringing payloads back down to Earth. However, that's happened maybe half a dozen times with the shuttle. And when that capability isn't available, it hasn't especially been missed a lot, because most of the time, if you have a free-flying payload, it can be attached to the outside of a space station, and you don't need to bring it back in such a colossal space that the space shuttle provided. So with those out the way, for reference, this is the X-33's tank, which was built and provided a lot of issues because carbon fiber and funky shapes in cryogenic temperatures don't enjoy themselves. So with all these problems aside, what's left to be used? Well, quite a lot. Shuttle and Buran's side saddle sort of spaceplane booster attachment worked quite nicely. The vertical takeoff, horizontal landing was very convenient. And with Buran specifically, only using its engines when it got into orbit, it meant that the rest of the vehicle could be used as a launcher, super heavy launcher in its own right, which worked quite nicely in for other projects that didn't require the orbiter. Notably Polyus, which did eventually fail, but the point stands. We have horizontally launched, horizontally landing spaceplanes, such as the sort of cousin of Skylon, the design study by Reaction Engines called Galactic A2. This was a sort of hypersonic airliner-going spaceplane, which used their Sabre air-breathing rockets to essentially make a suborbital spaceplane airliner, point-to-point transport, which is a very promising use for a spaceplane. Interestingly, the vertical launch, horizontal landing, reusable multi-stage spaceplane was a concept looked at as Mustard. The multi-unit space transportation and recovery device trips off the tongue. Totally wasn't intentional to spell mustard. Spaceplane that could carry a good payload mass fraction, at least on the concept, because it was multi-stage, and could return them because it was a large lifting body vehicle. But more about that later. Now, as you may have seen when I accidentally switched onto it, bit of bias, destination propulsion. As you heard in my wonderful introduction, I am working on destination propulsion at the moment. So I will want to work on destination propulsion wherever possible. So I will be showing this in a slightly more positive light, perhaps. Rotating destination engines, my field. They can outdo, or at least, why isn't that? There we are. They can provide the advantages of a jet engine without carrying all the turbo machinery that comes along with it. Because turbo machinery does not enjoy being blasted with Mach 7 air, and it is heavy. So if you don't need to carry it, you probably don't want to. They also have the advantage of being continuous combustion engines, unlike something like a pulse detonation engine, which has flown in the past. And they have a wide range of throttle settings available because you can have multiple waves traveling at once, as well as a broad propellant choice, because the injectors can be changed depending on the propellant you're using, and the only thing that changes then is essentially a software update. So how do they work? Rotating destination engines compress their fuel oxidizer mix instead of with a compressor just squishing them mechanically with a detonation wave. The destination wave is continuously traveling around the combustor, so you can see the animation at the bottom. And the majority of the combustion happens within the red detonation wave, producing a supersonic exhaust, which is back down at more or less ambient temperature pressures. So you can have a chamber pressure of 1 or 2 bar and have the combustion happening at approximately 40 bar. And you can do that without a compressor, which provides a lot of savings. So my engine is a little bit different. It combines a pulse detonation engine for augmented low speed thrust, rotating destination ramjet for higher thrust at higher airspeed from sort of Mach 0.4 upwards, and then a closed cycle air breathing rocket, so rotating detonation rocket that would be, for thrust in vacuum or very high thrust for takeoff. Here is a render of a now slightly out of date, I apologize, prototype, which we can look through by numbers. Currently, it's looking at a maximum of 15 grams per second of propane with up to 83 grams per second of oxygen or air, and air of currently unknown amount, because we're currently looking at the system for air supply. This will be a static testing system. We are expecting about 210 newtons at about 256 seconds of specific impulse at sea level, without a nozzle, that is, and about 190 newtons, 1300 seconds specific impulse predicted for the air breathing mode. So 1300 seconds is probably not very good for a relative to a conventional jet engine, but compared to a rocket, it is very good. It has a shock velocity of about 1700 meters per second. So that will produce a frequency of about 6.3 kilohertz, which is very, very high compared to a pulse detonation engine. So you're not going to have issues with vibrations so much when you are operating this mode, which is a good thing. I'm going to pause here and answer a question. What is your view on the supposedly anti-grav and hypersonic vehicles seen a lot on CNN and Fox News? I would not know about the anti-gravity engines. I do not know if they're a thing, so I'll be very interested to see if CNN could find a source for that. But there have been a lot of hypersonic tests going on lately with scramjets, which are a bit of a faff in their own right. They have to be going supersonic before they operate. So I haven't really touched on them much here because they're sort of a presentation in their own right. But they are relatively promising for space planes. However, using a good-sized space plane with a scramjet means you need an equally huge booster to get it up to a supersonic speed. So they are less ideal than a lot of the other propulsion systems we've touched on today, but they sit in the air-breathing ramjet sort of area. So here we have a ramjet which produces static thrust all the way up to essentially as high as your shock diffuser can get you, so Mach 7, Mach 10. More information on scramjets, sorry, I've had another question. More information, could you elaborate?
Sorry, William, that was aimed at Mr. or Mrs. or Miss Anonymous to see if they can give you more information.
Ah, sorry, I see. Well, in that case,
that's okay. I think we leave the Q&A to the very end. If you just
thought I'd touch on it briefly. Okay, so we have currently an engine compared to a scramjet that can operate from essentially standstill to very, very high Mach number without needing to be boosted up to the speed of sound, which means you don't have the extra stages that are essentially superfluous in this sort of flight model. So applying this engine to a spaceplane, what would you want in the current environment? Well, you'd want it to have as little internal structure as possible. You wouldn't want insulation between your fuel and your oxidizer, that sort of thing. So having tanks able to be within one another would be a good thing. That's why I'm using propane, because propane and oxygen can be liquid at the same temperature and pressure. Fun fact for you there, which means you can essentially have a bladder inside your propane tank carrying a little bit of oxygen as needed. A little bit of oxygen if you're using air breathing mode. So most of your oxygen is coming from the air. So you don't have to carry it with you, which means you have a better payload mass fraction or better delta V, depending on what you want out of your spaceplane, because you're not dragging along extra oxidizer, which you are also spending oxidizer to fly through. You want an air-breathing vehicle, again, air efficiency. You want it to be multi-stage, because single-stage orbit vehicles suffer from an awful payload mass fraction. So multi-stage means a slightly cheaper system. You want it to be fully reusable, because at this point, expendable vehicles are starting to look a little bit old-fashioned. When you start dumping bits of your rocket into the sea, it's a waste of money, it's a waste of material, and the fish probably don't appreciate it. So having all of your vehicles either be recovered or landing again is essentially what we should be aiming for. We want it to be vertical takeoff, because launching that way and then having to go that way means you are dealing with a lot of drag to bank up to the direction you want, as opposed to launching upwards and then using a gravity turn to bank over, which is a lot more efficient. And for the sake of argument, we want a lifting re-entry. We like the nice volume to area ratio, and we like the low g-forces. So sure, the space shuttle in its decades only recovered payloads, maybe free-flying payloads, maybe 6 times, but 6 satellites is better than none. So we want vertical takeoff, air breathing, multi-stage, fully reusable. That sounds a lot like mustard all of a sudden. So maybe there's a day for it yet. Maybe this is what the future of spaceplanes will look like after all. But in the meantime, I guess I'll keep working on it, and hopefully we'll find out at some point. Thank you for your time, and now I believe we have a bit of time for Q&A. If anyone has anything to raise or any points they'd like to discuss.
Hey William, that was absolutely great. Your enthusiasm shines. You are a young man, clearly with a career in front of you. I'm towards the end of my career now, and I'm a bit of a history fanatic. I'm just gonna say something that I think is really important. We, the United Kingdom, had an absolutely wonderful history in this subject. When the guys from TSR2 were made redundant at Wharton, they were put on to something called Project, I think it was Project 4042, which was Mustard, the Mustard series of projects. And I'm going to quote something. I've just walked to a book on my bookshelves. I'm going to quote something. Between 1963 and 1966, English Electric and BAC at Preston led the world in reusable spacecraft design. Mustard predated the US Space Shuttle by over 6 years. I mean, we have a tremendous background in this. If you're part of the new generation, please take it forwards. I've got a couple of questions. We're looking at, again, the historical aspects. Do you want to talk to us about Mustard for a little while? Mustard, I worked at Wharton, so I'm a bit biased. Go on, talk to us about Mustard.
Well, you'll probably see from things like the M52 in the background, I still hold a grudge that Mustard was cut short, and similar related vehicles, TSR2 is included. But Mustard is one of my favorite space concepts because it is really good. It does everything you want from a space plane, not just in 1963, was it? But today still. It had the low re-entry forces because it was a large vehicle, and on re-entry it would not carry a whole lot of fuel, so it would be very low density, so it would have a very, very gentle return, similar to there's a very nice picture over there. Is that a sorry, you're very little. Let me zoom you in. I have read that book, yes. It is, I cannot recommend, if anyone is looking at it, to read that British Secret Projects book, because it sheds a lot of light on some really interesting projects over the decades that may have fallen by the wayside, but may prove inspiration to future concepts. But Mustard was essentially the idea that you could have one space plane that you make a few of, and you bolt them together and use propellant transfer to fuel one vehicle all the way to orbit and have the other two glide back down to the runway. Anyone's played Kerbal Space Program, which is a very good video game if you want to know more about orbital mechanics, will have probably used propellant transfer at some point. Unfortunately, it's very difficult in real life and very easy in Kerbal Space Program. It demonstrates the point quite nicely that if you have lots of tanks and you are trying to get one tank to orbit, dragging another half-empty tank is probably not a very good idea. If you have one full tank and one empty tank and drop it off, you are going to have a much more efficient ascent, which is what the guys designing Mustard realized very, very early on. That if you have 3 space planes, one is empty, 2 are full, the empty one drops off, you're going to ascend a lot more efficiently than flying up and dropping an empty tank to keep your half-empty rocket going, which is what is used by most vehicles today. It used hydrogen and oxygen, which was rather like the X-33 and Venture Star, which it sort of gives X-33/Venture Star vibes if you look at it, compared to the Venture Star, with the exception of the lack of the the linear aerospike, which is probably a good idea because they're a bit of a pain as well. Unfortunately, I like them rather a lot. But yes, I probably am not the expert on Mustard compared to that book that was shown just now, British Secret Projects, I believe it was called, and I've forgotten again. So I will deal with some other questions, but I cannot recommend enough to look into it in a bit more detail in those books. So, from Philip
Okay,
Lim.
I've got one here from Philip Lim.
All right, sorry.
After the presentation, are you aware of any green propellant or low toxicity propellant projects? Who do you think will win the space race? USA, Europe, India, or China? Okay, let's ignore the green propellant because he's asked you to come back to him after the event. But talk to us for a second about as a young man just entering the field, who do you think is running fastest at the moment? Who's likely to win, and what are the projects you see the most prospect of succeeding?
Well, winning the space race really depends on where the finish line is, I guess. If it's the space race, I think it's pretty conclusive that the Soviet Union won that one. And we're all a bit late for it now. But to the moon, I wouldn't be surprised if the combination of Russia and China got the first, I don't want to put money on this, but the first settlement on the moon, while the US and Japan and that coalition have Gateway in orbit, and hopefully they will work together. But precedent does not bode well. But that is my theory on who will win. Russia, China are working together on the ground, on the moon, and the US, Japan, and co working together in orbit around the moon. But also, I'll look forward to your answering more about the green propellants, because I did a bit of research on that a while ago as a different project. So they are very interesting, and hopefully will be used a bit more in the future, because when things go wrong, it's always nice to have the safety of not dissolving in your propellants, just as a rule.
If you have something to add there around green propellants, do you want to talk for a little while now?
Of course, yes. So I am aware of some green propellant projects. Suddenly, of course, the moment I start talking about it, the name of the propellant has disappeared. I think it was something called like GP P2 or something like that. It was like the green propellant, and it was talking about using it was an organic molecule as a more or less hypergolic fuel oxidizer mix that was showing some promise. But actually, bizarrely, I don't think we'll be worrying about hypergolic fuels for much longer, because electric propulsion is coming along leaps and bounds, and using seen some interesting research using liquid metals as the propellant for electric propulsion. Knew some people at Southampton working on that, and that is extremely promising. I had a bit of nerd out with them a while ago, because I did my dissertation on liquid metal pumps. So I was like, yeah, I can pump your liquid metal into your engine. We could get extra thrust. So that's very exciting. So I would say the most promising up and coming green propellant is maybe bismuth. Oh, bismuth. It is a metal at room temperature. It's metal. It's always a metal. It is a solid at room temperature, but it melts at about 80 degrees to form a liquid, which can be accelerated in a magnetic field and thrown out the back of your spacecraft. This is quite dense because it's a metal, which means you have a good mass flow rate coming out of your engine, and can produce quite a sizable thrust, sizable for electric propulsion, and would be quite good for spacecraft in the future. So definitely worth looking into. Also, it's a metal, so it's sort of difficult to pressurize, but can be moved with an electric induction pump. So pros and cons. Okay,
thanks for that. You went on to electric. Yeah, you went on to electric propulsion there. There's another question here, which I guess is ions, etc., which you could almost call electronic, but we'll see what your comments are. Could a space plane use a solar sail?
The short answer is yes. The long answer is yes, but you may not want to, because space planes are really good at going to orbit and coming back down. Once they're in orbit, they're kind of inefficient because they're designed really beefy, got heat shields and heavy structures so they can survive in gravity that you don't really need in space. Solar sails provide a tiny little bit of propellant as thrust, very efficient, and but they're really, really good for spacecraft that are really light. Spaceplanes generally are not that. So although you could mount it to a spaceplane, you probably would want to give that a miss and just pack a slightly bigger engine. Deploying a solar sail, definitely possible if they were to launch a smaller spacecraft into orbit.
Okay, next question I've got here. Fazar Abel asks why several smaller space planes, such as Virgin Galactic's SpaceShipTwo, does not use tiles for heat shielding during re-entry, unlike the larger space shuttle. So I guess the question is, why don't space planes use tiles?
Well, spaceplanes do use tiles. The difference you're noticing here is a difference in heat loading more than a difference in vehicles. The space shuttle used tiles because it went into orbit. So when it came back from it, so its re-entry started at Mach 25, so ridiculous speeds, and had to dump a lot of this. You think this weighed as much as like a 747, and it is traveling at 25 times the speed of sound. It has a lot of kinetic energy, which it then has to get rid of somehow. It got rid of it by turning into heat in drag as it burned through the atmosphere. Starship, SpaceX's reusable vehicle, also has tiles for the same reason. It is orbital and it slams through the atmosphere to try and slow itself down, which is why it has heat tiles again. Virgin Galactic uses basically its fuselage and maybe a heat sink because it is not orbital. It is not even close to orbital. It is very much a suborbital spaceplane. It goes up into what is space and comes down from what is space, but it does not go into orbit. So although it is high, it is not especially fast. It re-enters at around Mach 4, I believe. So it is well within the capabilities of sort of stainless steel and those sorts of materials. And I believe the first Mercury capsules, before they used heat shields, also used a heat sink because they were not orbital. So it's a matter of velocity more than lifting re-entry.
Yeah. Very, very clear answer. Thank you for that. That was great. Another question's come in. It's asking about weight savings in spaceships. What's your view of new materials? What's coming along? What might we see being used in spaceships in the future?
Ooh, that's a good one. New materials. Some really interesting metal and ceramic based alloys are coming through, and they're exciting because you end up with really nice light engines, which I know is not the thing you always think of, but making an engine nice and light is actually a very important thing when it comes to aerodynamic stability, because the lighter the back of your spaceplane is, the lighter the front of your spaceplane is, so it actually flies forwards. And metals that can withstand higher temperatures, metals that can stay stronger at higher temperatures are very, very promising. And the ability to use ceramics in place of metals in engines is very exciting, but also going to be changing a lot of how we think about engines. And a lot of that comes down to the ability to 3D print ceramics as well as 3D printing metals. So 3D printing is probably the main bit here, but the ability to shape ceramics and metals in shapes that were previously impossible to achieve, but also ceramics in general. So making your space planes out of China.
Okay, next one we've got here. We're going back to thermal shielding. So what alternatives are there, or are they being developed, to replace heavy thermal shielding?
Well, it's generally light thermal shielding. I mentioned mercury. Well, the mercury capsule used, I believe it was a copper heatsink with an Inconel or something liner over the top of it to try and keep it cool by all the copper soaking up the heat, and the metal protecting the very front of the back. Depends how you look at it. The forward end of the capsule during re-entry, and the replacement to that that heat shielding that isn't ablated, isn't lost like your average capsule, is a silica tile. It is a tile made of essentially a fancy ceramic, and it can absorb a lot of heat without burning or melting or liquefying. And they aren't being developed so much as they are being improved, because they've been used since the space shuttle. So I wouldn't say it's being developed. It already has been developed and is being improved, this sort of silica tile based heat shielding system. More than that, you probably want an active way of reducing the amount of heat you're going to have to deal with instead of reducing your shielding. Things like plasma actuators that can use that can push the plasma that you're forming as you go through the atmosphere away to try and slow you down faster than drag would, to try and reduce the heat load. But they are sort of a pipe dream at the moment.
Okay, got another one now.
That answers the question.
Yeah, thanks. That's again a clever answer. Again, it's nice to hear somebody who's close to being taught what the best technologies are at the moment. It's really handy to get someone at the start of their career. They're getting what everyone's being taught is the best practice, rather than.
I've done the last 4 years spent chugging through books.
Yeah,
I've chewed through a lot of this research.
Yeah, I understand that, and you'll continue. Don't worry. As an engineer for the rest of your life, you'll be chundering your way through books. John Axtell asks the question: what's your best guess as to what the USAF's X-37B does when it's in orbit? Oh, that's a bit of a naughty question, but X-37B, the secret aeroplane that the Americans are throwing up into orbit at the moment.
Well, it's either something very, very scary or something very, very mundane, and I don't think there's much in between those, unfortunately. It has deployed satellites. It's deployed small materials testing satellites, as we saw on the picture from OTV-5, and OTV-6, I believe, carried a different one. It's testing interesting electric propulsion, because the X-37B is in a good position to test different engines, because it's quite heavy, so it's not going to lose control. And you can bring them back down again and have a snoop around and see what broke. So it's probably a combination of classified advanced materials, like stealth satellites, interesting propulsion systems, so high efficiency satellites, and interfering with satellites, practicing orbital rendezvous and sneaking up on satellites. So it's probably more like a remote control satellite than it is a scary space plane. But yeah, it's probably a lot of materials and engine testing.
Yeah, that was a bit of a wide ball for you, but really, I don't think anyone was expecting a better answer than you gave. That was an excellent.
Fortunately, it hasn't gone to warp yet or anything, so we'll have to wait for
that. Warp! There we go. We're into when does the real world become sci-fi, or when does sci-fi become the real world? That's good stuff.
I mean, I can get food delivered by my phone, so I think we're already pretty close to sci-fi. So I don't know.
Totally agree. I'm going to talk for a couple of seconds just to pace us out. Talking of the history of why Britain was such a key player in the past, there's a very good Imperial College book called A Vertical Empire that goes into. Yeah, it's an excellent book. It looks at blue steel, black nights, blue streak, goes on to again the strange aeroplanes that were happening around the late 50s, so the Saunders Roe aeroplanes, the rocket planes, and then goes on to the BAE world, or shall we say BAC and English Electric as it was, of Mustard and Co. from the 60s. Very good book, that one. So that's another one that you space fanatics out there might want to read. Vertical Empire. Mr. Hill wrote it. I'll give all the details to William at the end. Not you, William, our William, so that he can perhaps put out the titles of those 3 books that we've been talking about. That was a bit of a paste, I'm afraid, because there aren't any more questions. I'm going to put a curveball at you. I've got 2 questions for you. The first one, what questions were you expecting to be asked today that you've not been asked?
Oh, I was expecting to be asked more about aerospikes, actually. I'm rather glad I didn't, because that's a whole another presentation in its own right. But yeah, I was expecting more questions on aerospikes, and I'm not sure. I was expecting the propellant questions, and no, yeah, I'm not disappointed by the questions that have turned up today.
Okay. I can't remember whether it was the last lecture programme year or the year before, but we had Sophie Harker on talking about reaction engines and Rolls-Royce and BAE. Sophie from BAE, she was then. That was a really good lecture to link with yours. It kind of links nicely. Reaction
Sounds like it, yeah.
Reaction engines. Have you had anything to do with reaction engines in your career yet?
I've met some people from there a few times. I've talking to the I met the guy from CEO of Airborne Engineering yesterday. I think it was the day before. And they're of course testing components for reaction engines of their Sabre engine. So I haven't dealt with them much directly, but I've sort of crossed paths with them a few times. But they are sort of the competitor. They are the ones doing the air-breathing rocket with big compressors and stuff, and I'm trying to make them look obsolete and old-fashioned. So hopefully I'll be dealing with them more in the future, but not much yet, no.
Okay. Thinking back to my past, when I was at university, a chap called Brian Thwaites was dealing with external burning of what were going to be suborbital hypersonic vehicles going to Australia. Have you had anything to do with external burning?
A little bit, yes. So you're thinking sort of single expansion ramp nozzles and that sort of thing. A little bit, because originally when I was looking at the engine, I was trying to think a little bit more deeply how to integrate it into an airframe and the full flight regime. And when you start to get to sort of above Mach 7, really, you can't sort of have an engine on a nacelle isolated from the rest of the vehicle. Your vehicle has to be the intake and the exhaust. So I did look at the sort of nose shockwave intakes and single expansion ramp nozzles, and I was looking at having a really rich, fuel-rich combustion mixture, and then a secondary burning for boosting up to high velocities. But then I realized when you're getting fast enough to use those sorts of technologies, you're probably going too fast in the atmosphere, and you should probably be a little bit higher and not wasting that much energy on drag. So I went off the idea in the end. But no, they are really exciting technology there. I quite like them.
Right, here we go then. Last question. So it's one from the audience again. Itmar Attia. What do you think would be the ideal aerofoil geometry for space planes, considering CG, centre of lift shifting with speed differences?
Well, that's an awkward one because, as you saw from most of the space planes on here, well, aerofoil geometry is sort of a non-existent.
Yeah.
because most of their wings are their body. So either blended wing designs or just lifting body. So I would probably say if you're dealing with center of gravity, center of lift shifting issues with a spaceplane wing, you're probably getting to the point where you shouldn't be using a wing, because they're either a fin for aerodynamic loads when you're going sort of that way, or they are getting in the way, essentially. So as little curvature as possible, because you are going from subsonic to hypersonic and everything in between. So either flat or very slightly curved for structural purposes, but otherwise lifting body seems to be the best option.
Yeah, I kind of guessed that was where you were going again. They haven't really got wings lifting bodies, but they do have a foil section. Right then, that's it for the questions. Let me move on.
God, there's a space plane with a wing. But I don't. There's a space plane with a wing on the front cover, but I'm afraid I don't know what wing that's using. It's more like a Learjet.
It is.
It's completely opposite to everything I've been saying.
Okay. I didn't think of that either. So you're not unique. Right then, on behalf of the committee and the members of the London Heathrow branch of the Royal Aeronautical Society, William, I've got to thank you for giving up your valuable time in order to tell us all about space planes. I wish you all the luck and health for 2021.
Very much.
And the greatest success for the rest of your career. Your talk was informative. You showed a tremendous amount of enthusiasm that I expect of young people. You're exactly what the future of our industry needs. Thank you very much indeed. Thanks very, very much for talking to us today. Okay.
Thank you very much for having me.
Yeah, it was great. Thank you also to our William, our Honorary Secretary, for undertaking the administration which made this lecture possible. I also wish to thank all of the members for attending this lunchtime event. I hope that you've all learnt as much as I have. Unless we get an offer of a one-time lecture at short notice, I've got to inform you that this is going to be the last lecture of our season. We expect our 2021-22 lecture season to start in September, so watch out for the branch news and the calling notices from William, our Honorary Secretary, in an email. Finally, I look forward to seeing you all again very, very soon, and I wish you all good health and good luck for 2021. William, over to you.
Thank you, Peter. As Peter says, this will be the last event of our branch for the given seasons, but we do encourage you to join us on the above social media channel. Visit our website for the latest information. I would also like to remind you the main society does have a lot of events throughout the summer as well. Please visit the aerosociety.com for further information. Thank you for joining us today. Goodbye.
From across the globe, from the centre of aerospace, and now to you.
Thank you for downloading from the Royal Aeronautical Society. If you enjoyed this content, please consider showing your support for the Society. Share a link to this presentation by email or on your favourite social networks. If you have an interest in aerospace, consider the professional and personal benefits of membership. Visit www.aerosociety.com.